Have you ever seen a headline about some new study and just wondered, how did they actually figure that out? How does a simple question, just a little spark of curiosity, get turned into a real data-backed conclusion? Well, that is exactly what we're going to unpack today, the powerful step-by-step process that we call the scientific method.
So let's start with a question I'm pretty sure we've all asked ourselves while cramming for an exam. You've got your favorite study playlist going and you're wondering, is this music actually helping me focus, or am I just kidding myself? It seems like a simple enough question, right? But it's the perfect kind of question to tackle with science.
All right, to get our answer, we're going to follow this clear 5-step path. We'll start with that initial spark, turn it into a solid hypothesis, then we'll map out a research blueprint, actually gather and analyze the data, and finally, the most important part, we'll figure out what it all really means.
Okay, first things first. A vague idea like music helps me study isn't really something you can test. Science needs to be way more precise than that. We have to sharpen that fuzzy question into a clear, measurable statement. And that statement, my friends, is called a hypothesis.
So what is a hypothesis really? The easiest way to think about it is as a very specific, educated guess. It's not a question anymore. It's a bold prediction about how two things are related. In our case, listening to music and, of course, test scores. This one statement becomes the absolute foundation for our entire study.
Now, here's where things get really interesting. In the scientific process, researchers don't just test their one great idea. They actually pit two opposing ideas against each other. First, you've got the research hypothesis. That's our prediction that, yeah, music improves scores. But then you have its rival, the null hypothesis. The null basically says, nope, there's nothing going on here. Music has no effect. The goal isn't just to prove our idea right. It's to gather so much convincing evidence that we can confidently reject that null hypothesis.
Okay, so we've got our competing hypotheses lined up. Now what? Well, we can't just start testing people randomly. We need a plan. We need a rock-solid blueprint for our experiment that makes sure our test is fair, effective, and will actually give us a clear answer.
This right here is the classic game plan for pretty much any scientific study. We've already got step 1 on lock. So now we have to choose the right method, and that choice is going to shape everything that comes next, from how we collect our information to how we finally make sense of it all.
Our question is all about cause and effect, right? Does listening to music cause a change in test scores? Whenever you want to answer a cause and effect question like that, the absolute gold standard is the experimental method. It's designed specifically to isolate that one factor and see if it's truly the thing causing the outcome.
Okay, so any experiment really boils down to two key players, the variables. First, there's the independent variable. Think of this as the one thing you, the researcher, are purposely changing or controlling. For us, that's the music. Then you've got the dependent variable. That's the outcome you measure to see if your change actually made a difference. In this case, that's the final score on the test.
But how do we know for sure that the music made the difference? We need something to compare it to, a baseline. And that's where the control group comes in. Our experimental group gets the treatment. They listen to music. The control group, though, studies in silence. By comparing their scores at the end, any difference we see should, in theory, be because of that one single factor we changed, the music.
And we cannot forget one of the most critical parts of any research, the ethics. Before a single person participates, researchers have to follow a very strict set of rules. This means getting informed consent from everyone, having the entire study vetted and approved by an ethics board, and then debriefing the participants afterwards so they know what it was all about. Protecting the people in the study is always priority number 1. No exceptions.
All right, our blueprint is approved. The ethics are all cleared. Now it's time to actually do the experiment. This is where we gather the data that's either going to support our hypothesis or send us right back to the drawing board.
So obviously, we can't test every single student in the entire world. That massive group is what we call our population. So we do the next best thing. We pick a smaller, manageable group that represents that larger population. And this is our sample. The whole idea is that by studying this sample, let's say 100 students, we can hopefully generalize what we find back to all students.
Now for one of the most brilliant and powerful tools in research, random assignment. We take our 100 students and, totally at random, we place them in either the music group or the silent group. Why is this so crucial? Because it ensures that just by chance, all the other stuff, like how smart someone is, how much sleep they got, their natural study habits, gets spread out evenly between the two groups. This helps prevent those pesky, confounding variables from messing up our results.
Okay, so after our students study and take the test, we collect all the scores. And check this out. In our hypothetical study, the music group got an average of 88%, while the silent group scored an 81%. Now, on the surface, this looks great. It looks like our hypothesis was right, but we're not quite done yet.
This is the moment of truth. We have the numbers, but numbers don't speak for themselves. We have to interpret them so we can draw a real, meaningful conclusion.
This brings us to the million-dollar question in pretty much all research: statistical significance. Sure, there's a 7-point difference between our groups, but is that difference real, or could it have just been a random fluke, just plain old luck? This is what statistics are for. They help us calculate the probability that our result happened just by chance. And if that probability is super, super low, then we can be confident that, yeah, the music likely caused the difference.
But even with statistically significant results, one study is never the final word. Science is a team sport, and it's played over a long time. A finding gets stronger through replication. That's when other scientists, totally independent of the first group, can run a similar experiment and get the same results. And eventually, researchers might do what's called a meta-analysis, where they mathematically combine the results from many different studies on the same topic to get the really big picture.
And that really gets to the very heart of what science is. It's not just a collection of facts you memorize from a textbook. As this quote from Marcia McNutt puts it so perfectly, it's a method. It's a process for figuring out if the things we believe actually line up with how the world really works.
So the next time you see one of those headlines that starts with, "A new study shows," you'll know exactly what's going on behind the scenes. You can start to think like a researcher. You can ask, what was their hypothesis? Did they have a control group? How big was their sample, and was it random? You're now equipped to go beyond just reading a headline and start really critically understanding the science behind it.